Unit 3 has to do with polynomials. And so our introductory lesson today is going to be primarily focusing on features and graphical analysis of polynomials, which will help us in the long run on graphing and finding other characteristics. Read along with me. A polynomial is defined as a single term or a sum of finite number of terms. In mathematics, a polynomial is an expression consisting of variables and coefficients that involves only the operations of addition, subtraction, multiplication, and positive integer exponents. When you start your math, you're going to recognize that there are going to be some problems that ask you to determine whether or not the given expression that you see is a polynomial. So what I need you to pay close attention is that all the terms should solely be adding, subtracting, or multiplying with one another. And do not let exponents escape you, as exponents must be positive integer values and nothing else. So look to make sure that all that I've highlighted in yellow is being met in order to categorize it as being a polynomial. Now, once you have decided that if it is a polynomial or not, you are also going to have opportunities to either name or classify a polynomial. So these two different characterizations is what I'm going to need you to focus on. So let's see here. You're either going to name or you are going to classify. Now I need you to make sure you see the difference between the two, because sometimes it's easy to get them confused. When we talk about naming, I want you to see the word naming begins with the letter N. And so this helps you remember that naming has to do with the number of terms. When I ask you to name a polynomial, I need you to count. So you are going to look and see how many terms there are. If there are one term, you will name it a polynomial. 2 terms, it's called a binomial. 3 terms is a trinomial. And anything higher than 3, you will write the phrase polynomial of n terms. So for instance, if it was 6 terms you are looking or had counted, you will say, name the polynomial as such. You would write polynomial of 6 terms. Okay? Over to the right, we have some examples already worked out. Now what I want you to notice is that the second column right here, the degree column, I need you to just hold off on that a second and just focus on the given polynomial, how many terms were counted, and then the classification name. So the first example, they just gave us a constant. Obviously, that's the only thing we see. So there's 1 term, and that's a monomial. Now, notice it is a monomial because it's just a single term with no exponent that is negative. So we can deem it a monomial. Even though it's just a number, it's a constant, it still counts. Here we have 2x minus 4. So 2x and the negative 4 means there was a count of 2 terms. Ergo, while we have a binomial, look down to this example. We have an x cubed, a negative 4x squared, a positive 1, 3 terms. We call it a trinomial. And that's all it is. There's nothing difficult at all with regards to what is being required here. Again, all I'm asking you to do when you are naming a polynomial is to make sure that the naming matches the letter N to remind you that it's the number of terms you are going to be doing. So all you need to do is count. All right, let's go over now to classification. Classification, on the other hand, has to be done with regards to the degree. You want to find the degree, which in this case, the degree is going to be our highest exponent. You're going to look at every single term and find the highest exponent. If you find a degree of 0, you will classify the polynomial as constant. 1 as linear, 2 as quadratic, and so forth. So let's look at some examples over here on the right. Notice that we need to classify. So what we are going to need to do is find the highest exponent. So we're going to examine every single term. Well, there wasn't any terms here but the 5. But I want to remind you guys something here. When you guys have a constant and you tell me there's no exponent, actually there is. 5 is the same thing as saying 5 times x to the 0 power. Remember, any variable, any quantity raised to the 0 power, in essence, is saying 5 times 1. Don't forget, m to a 0 power is a 1. Any variable to a 0 power is 1. So here's an exponent property if you have forgotten it. So a constant has a degree of 0. A linear polynomial, well, if you look right here, I'm going to expand here to make it easier. The next to the 3x, or the exponent for the x, is invisible. So that's actually a 1. And this one here, remember, is x to the 0. So definitely the degree in this problem is going to be 3x to the first power 1. How about over here? We have x squared. Let me make this a little bit finer tip. We have x squared minus 4. Again, this 4 has an x to the 0 power. So between those two numbers, the 2 is definitely the higher number. So here's the 1, here's the 2 I'm talking about, and that leads to the name. Let's go down here. We look at the terms. So you keep looking at each term. That's a term, that's a term, that's a term. And when you're looking at the terms, you're looking at the exponents. And so what is the highest exponent? Well, obviously it's the 5. And because it's a 5, you are going to tell me it's quintic. So again, classifying polynomials merely means that you need to find the highest exponent so that you can classify it versus name it. Naming means you count. Okay, so please remember these two differences as to not get confused. The letter naming starts with an N, so number of terms is the one that you're counting. All right, so let's go down here, further down on your note-taking guide. You're going to notice that this section here is something of repetition, and it is found in Unit 1. So Unit 1 is where we covered this. I forget which section in Unit 1, but we talked about even and odd polynomials already briefly, and I need you to know the difference between even odd polynomial versus even odd degree. They're two different things. Okay, so again, the Unit 1 stuff is this yellow one, okay? Unit 1. So just in case you have forgotten, let's re-look at this. If we talked about symmetry, if your graph was symmetrical about the y-axis, remember if it was a mirror image over the y-axis, we knew that it was going to be an even function. And if it was symmetric about the origin, there was kind of a rotation around the origin, we talked about it being odd. So this over here on the left is the graphical analysis that we used in Unit 1. So when we were given a graph, we were able to just look at it and determine even or odd. But we also did the algebra, the algebraic approach. And the algebraic approach was the one where we will substitute negative x into the given function to determine if it was even or odd. So let's remind ourselves how to do that. So I'm going to come over here to the left and insert a problem just to teach you what I'm talking about, or reteach actually. All right, so we have f of x equals 2x to the fourth minus 3x squared plus 7. Okay, so here's an equation. So what you guys are going to do is replace every x with negative, just like I did here. Notice I replaced this x with a negative. And if I do it on this side of the equal sign, I've got to do it on the other side as well. I need to replace this x. I need to replace this x. And there isn't any others, so let's do that. So I'm going to put my equals 2. There's that arrow asking for replacement. Anytime you guys replace, please put a parentheses. Replacing that x, bring down my fourth power, minus 3. There's another replacing of an x for negative x. Close parentheses, 2 plus 7. So do the substitution process first. And after you substitute negative x, you will simplify. Simplify means get rid of all those parentheses. So 2 negative x to the fourth power becomes positive. And then we have negative x squared, right? We have this piece right here. Negative x squared is going to become positive, right? Because 2 negatives make a positive, right? So that's positive, but that has to multiply by negative 3. That positive has to multiply by negative 3. So that means it's going to stay negative. And then the plus 7 had nothing attached to it. It just comes on down. Once you have substituted negative x, I need you to compare. Take the one you just found, the f negative x, and compare to f of x. And you will notice that they are identical. So what you're going to say is, therefore, these 3 dots in math means therefore, it is going to be even because it's the same. And the way you say it is that you say f of x, the given function, is the same as f of negative x. And you are done. So same has to do with even. And if every single one of those switched, like let's say, I'm making this up by the way. Let me pick another color here. Let's say this answer right here had ended up being negative 2x4 plus 3x squared minus 7. I'm pretending that this was an option. I want you to notice how this negative 2x4 is opposite to this. Positive 3x squared is opposite to negative 3x squared. Negative 7 is opposite to positive 7. So that would have been an odd function. Okay? An odd polynomial, my bad. Or odd function, yeah, I said that right. So going back over here, just remember this means, hold on. This means you have to have the same answer. And this one over here is the opposite. Because that negative on the outside, that tells you in math that means multiply by -1 and it switches signs. So that makes it opposite. And if you have a combination, obviously you will say neither. Now let's move on and talk about even and odd function. Okay, so this is even and odd polynomial. but this has to do with even and odd function based on the degree. Is it an even degree or an odd degree? Now, it is what is going to be quite obvious, okay? If you need to determine whether something is even or odd, I need you to look at the degree. Remember, degree is the highest exponent. If the degree of the polynomial is an odd number, that just means that the end behavior is going to go in opposite directions. It's as simple as that, okay? If it is an odd number, it is going to be in opposite directions. Now, I'm trying to make it thinner, but it's not letting me do it. There we go. Opposite directions. Now, if it is even, I did it again. That's okay. If it is even, we know that the ends are going to point in the same direction, right? Here's that word again that I'm talking about. It's same, right? And opposite. So keep those little hints from not going away. So here the arrows were pointing both in the same direction, right? That's same, so that's even. Same direction, even. These are obviously in opposite directions, odd, odd. All right. And what do I mean by those arrows? Well, here's what I mean. You guys eventually will be graphing some polynomials, right? This is a polynomial. And when I'm talking about end behavior, I'm talking about this end and I'm talking about this end. That's what I'm talking about, end behavior. So literally, this piece right here, whoa, I did not mean to erase that. So this little piece, and how can I erase it? By, there we go. This little, it won't let, why is he erasing the whole thing? All right, well, what I'm trying to say is, it's a little aggravating. I don't understand. Oh, it's an entire stroke. That's why. Okay. So this little piece right here, I don't care about those. All right. All I care about are those ends. And so looking at this picture, one's going down and one's going up. That's odd. Okay. So what are we going to do with this knowledge? Let's go to the next page. Bringing back the table, not only does the table help us determine even and odd degree, it also tells us about leading coefficients. Now, when it comes to leading coefficient, I want you guys to please make a note for yourself that leading coefficient is always going to be focusing on the right arrow. Okay? I need you to focus on only the right arrow. So let's do here. Goodness gracious. Hold on. I'm struggling. All right, here we go. Leading coefficient. I need you to focus on the right-handed arrow. So on this chart, if I'm talking about the right-handed arrow, I'm talking about this one, this one, this one, and this one. So let's make an R here to make sure we are all on the same page. Right, right. Actually, I'm not going to write it there for a reason in a second. Let me do it from here. Right, right, and the right, and the right. So all of them, the pink is the right-handed arrow. So I want you to notice that if I tell you that a leading coefficient is positive, so for short, we're going to use LC, okay? If I tell you that LC is positive, that means that your right arrow is going up, okay? If you see that the LC is negative or less than 0, that means the right-handed arrow is going down. right? So whatever the right hand does, it helps dictate what the other arrow is going to do. Please notice that even always means the arrows work in unison, in tandem. So if your right hand goes up, the other one has to go up. If your arrow goes down, this one has to go down. Okay, so they always work in tandem together. They're joined. The odd function, if your right hand went up, because you always start with your right hand, that means the other hand goes down. Or if you're pointing downwards, the other hand is going to go left and up. Odd directions. So how does that help us? Let us do two problems. I want you to please notice that these two problems, whoops, wrong pen, are actually two different problems. So I'm putting a little divider here so that you know to keep them separate. So let's start with the graph on the left, the graphical representation. Is this going to be an even or odd degree? What is degree? Degree means highest exponent, right? But this is not going to help us. Highest exponent does not help us. The definition does not help us in determining whether or not it's even or odd. So we are going to resort to what we just learned, that arrows pointing in the same direction will be even and arrows pointing in the opposite direction are going to be odd. This arrow and this arrow are pointing in opposite directions. So the degree of this given graph would be an odd number degree. It would have to be an odd exponent, odd degree. All right, LC is leading coefficient. Remember up here I told you the leading coefficient is determined by looking at the right arrow. Well, what's happening to that right arrow? It is pointing downwards. So you get to tell me that the LC is pointing downwards, less than 0. Okay, it's negative. Let's leave right-hand behavior, left-hand behavior for a second. I'll come back to it. We're almost done, so hang in there. Let's move away from the graphical representation. So this was graphical. Why does it correct my P's? There we go. Here's a graphical, and then we're going to do the algebraic representation. The equation of the polynomial has been given to us. So again, degree and leading coefficient. So degree means highest exponent. So we are going to look at all the terms, and I can see that I have an exponent of 6, of 5, of 3, of 4, of 2, of 0, and of 1. So the highest exponent is definitely that first one with the 6. And by the way, side note, let's say you ended up with a leading term that was written like this. Okay, where this is the term all together. What you do to get the degree is you say 2 plus 4 and 6. 6 would be the degree of this entire term. You add all the exponents of the exponents in the numerator. Okay, so I know you get some of those in Delta Math, so I wanted to make sure. So negative 5x to the 6, negative 5x to the 6 is going to be known as the leading term. All right, the leading term dictates everything about what we're trying to find about the end behavior of our graph. So the leading term helps us find the degree. We found it to be a 2. And because it's a 2, we can determine whether or not the function will be even or odd. 2 is an even number. So we know that our arrows are either pointing both up or both down. Okay. The other 2's definitely get to be deleted because we know it's odd. So we know it's even. So they work in tandem. Now we have to decide which one of these 2 is the right answer, right? So degree helped us to eliminate the 2 of the 4 options. Leading coefficient. Well, the leading coefficient in this problem is a -5. Coefficient is the number that's in front of the x that's multiplying. Notice our leading coefficient of -5 is less than 0. So what does that tell us about our right-handed arrow? That when it's negative, the right arrow has to point downward. So now we know that this cannot be an option, and we focus on this. So here's what I want you to realize. Let's put this arrow, let me do it again over here. We have an arrow going down, and we have another arrow somewhere around going down. Okay, so here's the thing that I usually ask students. What is this arrow doing? Students will tell me pointing down. Even if I ask this one, they would say it's pointing down. So what I need you to understand is that these graphs actually have more than one dimension that it's moving at, okay? So look here. Wow, I think that's going to be really thick here. Oh, no, it's the wrong one. Okay, so let's start with this left arrow, okay? This left arrow is not only pointing down vertically, it is pointing to the left horizontally. All right? So recognize these like vector components. That arrow is going down and left. How about this arrow down here? It is going right and down. Okay? Think about it as a x and y axis, right? Like this is the x and the y axis. We can tell that the graph is going more powerfully in this direction and in this direction. Okay, so hopefully that visual helps. Now, once you have decided on where those arrows are going, you can do this to help you at the beginning, but then you probably will eventually get it and not need to do this. Pointing left means you're going negative. So negative infinity. Pointing downwards means you're going negative infinity vertically. Over here to the right black arrow, it's moving right positively, and it's moving down negatively. So how do I compose this picture into a sentence? So here's how you do it. You will start. They want us to start with the right end behavior. This is my right here. Oh, wow. This is my right hand error and behavior. So I'm going to do horizontal movement first. You always do horizontal movement first. And I write as x for horizontal movement approaches, well, it's approaching positive infinity. All of a sudden I forgot how to do, there's my infinity. Then I put a comma, just like you're going to do x comma y. That's what you're doing. You're telling me x is getting more and more positive. No matter how many times I plot points, they're going to get more and more positive, like this. Plot a point, plot another point, plot another point, and look how it keeps going down and to the right. Okay? Now what's happening to the y? The y's are therefore approaching more and more negative values. Let's do the left-hand arrow. Okay, this is the left. And we just do the same thing. You start as x approaches. So we look at our x. Our x is horizontal. What is it approaching? It's approaching negative infinity. And then y, what is it approaching? Well, it's going down. So we say negative infinity. And so that's how you write end behavior. So what I want you to notice is that the only thing you're really changing is this. What is your x becoming? What is your y becoming? What is your x becoming? What is your y becoming? Okay, you're doing x, comma, y. That's what you're doing. So every single time in those rectangular boxes, you're going to put either a positive or a negative infinity. All right? So that's how you do end behavior there. All right? You knew what's happening with left and right, so it's easy to write. Graphical then is so much easier because it's already written for you there. It's already drawn out. So let's see, this arrow up here, in the upper left, it is going left for horizontal movement, and it's going up for vertical movement. Okay, and this one down here, it's definitely going down. Let's erase my writing there for a second. We don't need that part anymore. Whoops, I didn't mean to do that. Okay, I meant to just erase a piece, and I erased too much. Let's erase this piece. Okay, so with this arrow right here, it is going down, and it's going to the right. Okay, so let's put our little infinity symbols since we're new at this. This x is going negative infinity. This arrow is pointing up, positive. This x is going to the right, and this y is going down. So we need to do the right end behavior first. Right end behavior, so we're going to work on that. And the writing doesn't change. You start as x approaches. What is it approaching? The one on the right is approaching negative infinity. Oh, sorry. I'm looking at the vertical. It's approaching positive infinity. Okay, did I confuse you? This is the right hand. So it's approaching positive infinity for the x-axis, comma, on the y, it is approaching negative infinity. And then we'll look at the other one upstairs. Let me minimize here a little bit. And we have, again, as x approaches, the horizontal is x, is negative infinity, and then y is approaching. Look at the vertical movement, it's going up, positive infinity. And that's it. That is how you do left and right end behavior. Good luck, and thanks for watching.